Okay.
Okay, so we started?
Yeah, that's what.
Okay. Okay, so I'm going to I'm going to try and follow up on something that we were doing the last time we talked, which was like 2 weeks ago, and I'm a little bit disorganized, but I think I can remember where we were. We were talking about special commutative Frobenius algebras. So in particular, I made a mistake. So I'm trying to fix a mistake here. And it was very clear that I made a mistake. We finished last time on like a mistake, and it was clear that it was a mistake. So now I'm just trying to fix that mistake. And then maybe we'll get onto other topics or get back to this topic, not quite sure. But so I guess the general topic is that we're trying to clarify the relationship between special commutative Frobenius algebras, roughly speaking, and on the one hand, and n-bang torsors on the other hand. And so I remember how this goes. I guess we construed this as a prop. So there's a prop for the special commutative Frobenius prop. And we also get a prop from the concept of an n-bang torsor. And there's a whole bunch of abstract nonsense here involving adjoint functors between doctrines and things like that. But let's see if we can get to this to be somewhat concrete. So there's like a okay. So I guess there's like I guess we're having a sort of prop homomorphism here. Let's call it H for homomorphism. And this, let's see. So I'm trying to figure. So I'm writing SC Frob, special commutative Frobenius, as the name of this prop that we're interested in over on the left. And I'm just trying to figure out how to notate this prop over on the right. I want to say that it's the concrete prop of the, I guess we're calling it the tautological representation of n-bang. And so these particular props are vector-valued props, vector space-valued props, or whatever we call them. And so maybe I'll say, this is very ad hoc notation. I'll just say C for concrete. It's the concrete prop of, in this case, meaning of all the invariant tensors on the what we're calling the tautological representation of n-bang. So that tautological representation, that is the n-dimensional representation. N-dimensional representation. And so we're interested in this idea of explicitly describing the kernel of this prop homomorphism. And there's a whole bunch of ways of thinking about and approaching this problem. There are more abstract, more concrete ways. And we have some vague ideas about how to relate this to some stuff about the Doppler-Roberts theorem. Is that what it is? Yep. But and to relate it to stuff like that. But at the moment, I just want to describe very concretely an extra law that holds in this concrete torsor, the concrete prop of that you get from the concept of n-bang torsors. And so I tried writing it down at the end of last time, and I sort of got it backwards. And let me try to write it down, and then we'll try to understand where it's coming from. So let's see. So let's see. So we're dealing with Frobenius algebras. So they have multiplication in them, and they have unit, and they have co-multiplication, and they have co-unit. And roughly speaking, we need to notate that kind of stuff. But for the example that we're going to do here, I think all we're going to need is something like notation for multiplication, which we'll just use as juxtaposition, just writing things next to each other. That's multiplication. And for co-unit, that's the only other thing we're really going to need in the notation, is I'll just use brackets or round brackets around something, meaning, evaluate the co-unit at that vector. And so let me see if I can remember how to write this down. So how does it go? It goes, so trying to remind myself how this works. This is a sort of, what's the buzz name I'm looking for? Möbius inversion. This law is arrived at with the help of some Möbius inversion. So the idea is that there's sort of Möbius inversion between two bases for the special commutative Frobenius prop. And so one of the bases is, what do we call it? I guess we call it the Frobenius basis, I guess. And the other one is what I'm calling the Hecke basis. And the Hecke basis is really adapted in some way to this idea that we have a prop homomorphism here, because the Hecke basis consists of these elements that I'm calling the Hecke tensors, which are like a tensor analog of the Hecke operators. You can think of an operator as a 1, 1 tensor, and so a Hecke operator is an example of a Hecke tensor. But we have Hecke tensors with different numbers of input and output indexes, not always just 1, 1. And so how does this work? It's like, what am I trying to say? So we're interested in lattices of equivalence relations here, right? That's very related to the special commutative Frobenius prop. Well, right. I mean, so okay. So before you linearize the special commutative Frobenius prop, it's like a set-valued prop, and its elements correspond to isomorphs and classes of cospans. Is that right?
Yep, I think so.
Okay, and that's almost the same thing, depending on how you feel about almost. That's almost the same thing as what do we call those? Correlations. And the only difference between the correlations and the cospans is that the general correlations can have these extra.
The general cospans.
Say that again.
The general cospans.
What did I say?
I thought you said the general correlations.
Okay, sorry. So yes, the general cospan that has these these extra
unrelated elements.
That's what we call them, unrelated elements. They don't really participate. So I guess we talk about the apex or maybe the co-apex of the cospan, and there can be elements in there that are just not in the image of anything coming from the legs of the cospan. And we can think of the correlations as being the cospans that where that image is empty, I guess. No, where that empty, right, where the non-image is empty, where the image is everything, right.
Mm-hmm.
And so for the correlations, it's a finite combinatorial problem. Whereas for the cospans, it's just, right? You can have as many, you can have an infinite, well, you can have as large a finite number of these ghost particles or whatever we call them. But so, right, I guess you pointed out that when we're well, okay, and we know that we know that our image prop does have finite dimensional operation spaces. So obviously something has to give there, but you already explained that, right? So what did you tell us? That the extra particle sort of turns into a factor of the dimension n. Is that correct?
I would have to check that, but I think so. So yeah, I mean, when you have a loop, which is the kind of thing you can do in a cobordism,
yes,
then that gives you a factor of n. And then in a special Frobenius algebra, the loop is equivalent to a sphere or a point or whatever, depending on what your image is. And so well, I'm acting like that's still the dimension n, but I actually would have to check to see if that's true. But it should
okay. We could put that aside as a separate question that we don't have to worry about right now, because it is a slightly different from the main question that we're supposed to be focusing on. But that's one of the questions that's involved in understanding the kernel of this homomorphism, is understanding what happens to those extra particles.
Yeah.
Or just along for the ride.
I think it has to give you some scalar, and so it doesn't matter to us too much what that scalar is right now.
That's right. But I think it probably is n. Okay, so once we've put aside those extra particles, and we're really now just dealing with correlations. So correlations are really just, am I saying this right? That sounds funny. Correlations are really just equivalence relations. Why does that sound so strange? Correlations are equivalence relations on the sum of the domain and codomain. And so there's a lattice of those correlations. And it turns out that when we're dealing with this prop homomorphism, it's useful to think in terms of Möbius inversion with respect to this pair of bases. Well, this lattice. What am I trying to say? That can you describe how this is supposed to work? What am I trying to say? That
You're trying to describe how you get the Hecke basis from the Frobenius basis.
Well,
Describe it.
I'm trying to sum up the whole big conceptual picture without getting into too much of a rabbit hole here. But what am I trying to say? That well, I'll try to do the example. I'll try to do the example, and then we'll try to appeal to the example to understand the Möbius inversion philosophy here. I think that's how I'll try to approach this here. So the example that I've got here is let's say, for example, let's say n equals 2. So basically, we're thinking of two-dimensional special commutative Frobenius algebras. And so an example would be like the complex numbers as a special commutative Frobenius algebra over the real numbers.
Mm-hmm.
And so of course it's a commutative algebra. Of course it's a commutative algebra, but it's also got this co-unit operation, which basically gives us this special commutative Frobenius structure. And that co-unit operation is basically just the sum of the conjugates, the sum of the conjugate pair of complex numbers that give the real number. So in other words, am I saying this right? That's just when you add the two conjugates of a complex number together, you're really just getting twice the real part.
Yeah.
So that's this Frobenius co-unit. Okay. And so that operation, that Frobenius co-unit operation, satisfies all the Frobenius, the whole algebra satisfies all these Frobenius laws, all the laws that are summarized in this Frobenius prop, but they satisfy something extra. They satisfy some extra things. And I'm trying to explicitly write down one of the important things that they satisfy here. And so it goes, let's see. So what does it say here? So it says A, B, C minus A, B, C minus AC, B minus BC, A plus, let's see. So, okay, how is this going to work here? Let's see. So,
does parentheses mean the co-unit?
yes, it does.
Uh-huh.
Parentheses means apply the co-unit. A juxtaposition like A, B next to each other, that just means multiplication. So
if A and B and C are all 1 in the complex numbers,
yes,
then the parentheses around a 1 gives you a 2, because you said twice the real part.
I guess that's right. Yes.
So we're getting 8 minus 4 minus 4 minus 4 so far.
Yes. Yes.
Okay. Plus 2.
Well, I'm trying to figure out the coefficient on this thing. So first of all, you from staring at this, you can already see that this looks like it really is Möbius inversion over the lattice of equivalence relations on a 3-element set. I mean, we're dealing with n equals 2, but that means that a certain ternary operation is dying because 3 is bigger than 2, and that's what we're trying to write down here.
I mean, I just showed that if this stuff is equal to 0, then you need to have a 2 in front of that last term.
That's kind of what I was expecting, but does that really work out? So what are you saying? You're saying 8 minus 12 is negative 4 plus. Are you getting the 2 to work out there?
The real part of 1 is twice the real part of 1 is 2. I'm just looking at the case where A, B, and C are all 1.
2, 2, 2 is 8. Okay. 8
minus 2 cubed minus 3 times 2 squared is negative 4.
8 minus 4 minus 4 minus 4.
So now we have to get plus 4 or else we're dead.
Well, I think this is right. I think this is correct.
So hopefully you got it from some completely different reasoning, like Möbius inversion type reasoning.
Yes. I mean, so basically the stupid mistake I made last time was, I think, so first of all, the lattice of equivalence relations on a 3-element set annoyingly looks rather similar upside down. And that's the mistake I made last time. I got the lattice of equivalence relations sort of upside down. So, in this hopefully correct version of the formula, it looks like we have the finer equivalence relation over on the left and the coarser equivalence relations over on the right. And I just got that backwards or upside down the last time I wrote this. But this really is working. And
I mean, in what sense is it working?
So, well, if I didn't screw up, this works in any two-dimensional. Well, this is in the kernel of the prop homomorphism that we're interested in here. But in practical examples, that means, for example, that it holds in the complex numbers, for example, or it holds in any quadratic extension field. Or is there any extra word that any adjective I need to put in front of quadratic extension fields? I think any reasonable quadratic extension field where you take the Frobenius co-unit to be this so-called trace, which is the sum of the two conjugates.
So now you're touching on this question I had that we're supposed to talk about in part.
Yes.
Which is, what do G torsors have to do with field extensions? And so
that's right. And one of the ways to answer that question is to also drag in these special commutative Frobenius algebras, which I'm actually sort of blaming on you for having dragged in the first place. But yes, all these things are very closely related. Yes.
So anyway, so far what you're saying, not to feed in any more to what you're saying, what you actually said, is that any quadratic field extension of your original field gives you a 2-bang torsor over that original field.
That's right. That's right.
And what does that mean? That just means it gives you a vector space that's acted on by Z mod 2 in some kind of in a way that's
something like that. It does mean something like that. There are some very abstract ways of describing what it means. There's some very concrete ways of describing, well, some relatively concrete ways of describing what it means, more abstract ways of describing what it means. And this is a question that you're really trying to bring up here. And I do want to switch the focus to that question just in a moment. But before we switch the focus in that direction, I just want to finish correcting this mistake so that we can get to the question that you want to talk about.
Okay.
So I think I'm mostly done just correcting this mistake. So, this is it. This is I believe, the correct version. If there aren't any additional mistakes that I have just introduced, then this is the correct version. And you can, in principle, you can see, if you can stare at it enough, you can see how this really is using a Möbius inversion.
Could you just draw? I don't actually quite see it, although it certainly looks sort of
The lattice of equivalence relations?
Yeah, if you could draw that lattice, then I could maybe.
Okay.
So you want to have the
Again, I think this is where I got in trouble last time, was actually drawing. I guess I want to draw the finer equivalence relations going upwards, I guess. So it's like A, B, C, and then A, B, C, and A, C, B, and B, C, A, and E, B, C. So this is the lattice of equivalence relations, and I guess it's a, what is this? This is a distributive. This particular one is distributive, but non-modular. No, modular, but not distributive, I guess. Is that what it is? I don't know.
I mean, it couldn't.
That's a digressive question. I shouldn't worry about that. But
yeah, I think you're right. Yep.
So yes. So okay. So right. I think I've corrected the mistake. There's still lots of other things to say about this, but we're not going to try to say much about this right now. We're going to try to switch to the question that you were just hinting at. So but just before we quit, let me mention that again, that there are, well, maybe I already said it. There are all sorts of interesting things to try to understand here. And some of it might include possible relationships to ways of understanding the Doppler-Roberts theorem and stuff like that. Yeah, we'll put this aside for now. And let's try to get to this other question. So, okay. So the question now that you brought up in email was, in some sense, why torsors? So this is, I've been talking about torsors a lot. And John has now been asking me, why am I talking about torsors so much, or something like that? And I'm not sure I completely understand the question, but
I keep asking it.
Yeah.
Let me ask it so the world can hear it. So
okay.
So Jim was starting to try to get to some cool formulation of art and reciprocity, some better way of thinking about art and reciprocity.
Better in the sense that I could understand it. Yes.
Right. Yeah. And I don't know if you've ever told me what it is, this better formulation, but it has a lot, but apparently it has a lot to do with torsors, because you're talking about torsors all the time. But I just realized while watching so we had a previous episode where I was asking, where I was trying to summarize what you were saying and then get you to correct my summary. And I just reviewed it in order to write down a summary of that episode. And it was very embarrassing to watch, because I felt like I was asking, probably because I'd already been through the conversation, but I'd sort of forgotten the conversation. But anyway, I was asking these, saying these things, some of which were fine and some of which just seemed really stupid, and then not letting you butt in until the end when you quickly corrected everything I said that was wrong. And what was that about? That was about torsors. And it explained a lot about what you mean by torsors for like a finite group. I think we limited ourselves to that case. But there wasn't enough time, except at the very end, to get into any of your proposed applications of torsors to art and reciprocity or anything like that. Actually, you did very rapidly say something, but unfortunately it wasn't detailed enough for me to reconstruct it. So I'm really still sort of mystified by what exactly is the way that torsors come up from, for example, field extensions, or maybe you were like saying maybe more general extensions that turn out not to be fields. That's the part that I really didn't quite catch, although I have a flavor of it in my mind. So anyway, I want to know anything about.
Okay. I'll try to give some sort of answer to this question. I still have the feeling that I have too many different answers to give, but as we go along, we'll maybe try to narrow down. Maybe as we go along, I'll get a better idea of which version of this question you're really asking here, so that I can give a better
anything. Yeah. Anyway, anything is better than what I have now, which is like
okay.
A mess.
Okay, so let me try this. So let me try this. Like I said, I have a whole bunch of different kind of answers, except that I think that there's one very commonly repeating theme in all of my answers, or almost all of my answers, which is to think about analogies to homotopy theory, or something like homotopy theory. So what I have in mind is that there are various kinds of analogs in algebraic geometry and or commutative algebra. There are analogs of the idea of the fundamental group of a space.
Mm-hmm.
Maybe we should emphasize the fundamental group of a space at a base point or something like that. So So let's think a little bit about what that means. Okay, so well, actually, I'm trying to think of like what's some of the relevant terminology here. Sometimes people talk about something called an absolute Galois group. Is that right?
Yeah.
Now I'm trying to figure out how that parses. Like maybe it's the absolute Galois group of a field or something like that.
Certainly that is a primary case. Yeah.
Again, now I'm worried if there's some technical adjectives I should be putting in front of field or something like that. Because right, I'm tempted to say that this is something like the absolute Galois group of a field K. Yeah, I've put this. One of the reasons I'm putting this in quotation marks, this phrase absolute Galois group, is because I'm not sure I've really narrowed it down to exactly the right definition yet, but maybe we can sharpen it as we go along. So I want to say that it's something like the or something like the automorphism group of the, well, first I'm tempted to say of the algebraic closure of K over K. But there are all sorts of funny things about that. One of which is when you talk about the algebraic closure of K, that's already a little bit illegitimate, right? Because there isn't really a the algebraic closure. There are only algebraic closures.
Yeah.
And the other funny thing is, I'm suddenly really expecting you to say something like, oh, we're supposed to take the separable closure or something.
Yeah, that's what I would say.
which sounds like some technical detail that at the moment seems a little bit annoying, but I don't know. I'm not, how much do I have to worry about that? That probably will come up when we
If
think about
you're
separable the special commutative Frobenius algebras. But go ahead, yes?
if you are mainly interested in number fields, then you don't have to worry about that. They're the same thing.
Okay, then let's
Happy to ignore annoying issues like that.
then for now that seems good enough. But we're just reminding ourselves that there are things we're being sloppy about here, obviously. So, there are things written down on the screen here that might need a lot of fixing up to be technically correct. So it's something like, but we're saying it's something like the automorphism group over K of some sort of separable closure or some sort of closure of K or something like that, algebraic closure. And again, this terminology is supposed to mean something like the automorphisms that fix K pointwise, but they move the stuff in K bar around. We mentioned this about, we mentioned the idea about this being analogous to the fundamental group of a space at a base point. So one of the semi-obvious questions here is, what's the analog of the base point here? And that has a reasonably nice answer. I mean, if you think about it, it really does make sense that act of breaking the symmetry by picking a base point, that is equivalent to the act of randomly choosing an algebraic closure.
That's nice, yeah.
Yeah.
Like
and
favorite fiber.
yeah. And I mean, you can take that philosophy pretty far if you really want to. Like, I don't know, somehow the idea that, right, that a base point is a point-like, and the algebraic closure is more point-like than the original. K bar is more point-like in some sense than K was, because K bar doesn't have any what am I trying to say? It itself has trivial fundamental group, or it's or it's at the algebra.
Oh, that's sort of weird, because I tend to think of it here as being universal cover like, which
That's right. That's right. So it feels bigger, but it's co-bigger, and it's it's simply connected. The universal cover is simply connected, so that is actually more point-like than the thing that it's covering.
But it's covering the whole thing, and you were trying to pick a specific base point. It seems like a mixed metaphor. Yeah. Anyway.
All right. I'll have to think later about how well I understand what you're talking about there. But let's see. So yeah. So for fields or some kind of nice fields, this is the way that it works. And then there are generalizations that we're interested in. You mentioned more general fields where you have to worry about separable closure versus algebraic closure or something like that. And then there are things more general than fields, and we're interested in that too. And so what's the further adventures of this absolute Galois group as you generalize in those directions? And it's probably something like the étale fundamental group or something like that, of something that's more general than a field, or more general than the spectrum of a field, some kind of, I don't know, I'm not exactly sure what the most general thing is that can have an étale fundamental group, but there's probably something like that. So So, I'm trying to answer your question, why torsors? So what I'm saying now is that, first of all, we're interested in these algebraic geometric analogs of fundamental groups. We're interested in them, so absolute Galois groups and étale fundamental groups and stuff like that. We're interested in those. And you'll buy that, right?
Yeah, sure.
And so there are those groups that we're interested in them. So how are you going to understand some particular group? And, by some general philosophies of category theory, you understand an object by how it maps into other objects, or vice versa, how other objects map into it.
Yep.
And so that's going to lead us, that's going to provide us with certainly some ways of answering the question, why torsors? Because, so what we're saying is, looking at the torsors over K is really just telling you how to map the this fundamental group of the variety into something, namely into the group that we're considering torsors of. So, right, you can get a whole picture of the absolute Galois group by knowing, or you can get a whole picture of the this fundamental group of the variety, or whatever it's called, or the scheme, or that you can get you can get in principle, you can get a whole picture of the fundamental group of the variety or the scheme or whatever by knowing how that fundamental group maps into, well, for example, how it maps into arbitrary groups or arbitrary finite groups or arbitrary profinite groups or something like that. And basically those maps are the torsors. Right? I mean, right, when you map the fundamental group of a space into a group G, roughly speaking, what you're doing is you're studying the covering spaces. Sorry, not the covering space. You're studying the principal fiber bundles, the principal G bundles over that space.
Yep.
So I mean, that's, in some sense, that's the answer. I mean, right? So again, in homotopy theory, the answer to why torsors is because, well, torsor is just another name for principal G bundle. G torsor is just another name for principal G bundle. And it's just really obvious in homotopy theory that a good way of, studying the fundamental group of a space is to study the principal G bundles for lots of different G, for all different G over that space. Because that's really, and that's the homomorphisms from G. That's the homomorphisms from that fundamental group into G. Roughly. I mean, right? So you can say it, in a slightly better way if you pay more attention to, the yoga of category theory or something like that. So instead of just thinking of it as like a set of homomorphisms, there's actually, this groupoid of torsors, groupoid of G torsors over a particular space.
So okay, that's good. Yeah. So you're going to continue?
Yes.
Okay.
Yes. So I mean, but right, but
also, let me just
go ahead.
Okay, I mean, I like that.
Yeah.
So I'm thinking that these G torsors in this example here,
yes,
they will be, sorry, you're not going to like this, but okay, they'll be separable algebras over K whose automorphism group, or sort of fixing K. I mean, K is the field of ground field for our algebra. So, so the automorphism fix that. So separable algebras over K whose automorphism group is G. Those are the G torsors.
That's certainly something like that seems
right.
I
meant commutative.
There are all sorts of silly traps that I fall into here very often. Well, what were you going to say?
Commutative.
Yes, commutative. But there are silly traps that I fall into here on occasion, having to do with, I mean, you already hinted at this probably, whether you're looking at automorphisms that fix K pointwise or more general automorphisms.
Yeah, I really want to fix K pointwise. I mean, you're fixing K pointwise for this universal cover. Sorry, for this fundamental group. It's the group of automorphisms of this K bar that fix K pointwise. So these other G torsors over these other G torsors should also be doing that. Okay, but
I mean, again, you're probably jumping a little bit ahead to something I didn't quite want to get to yet, but it is important too. But I mean, you're saying that you're going to look at these torsors as separate algebras or something. Again, I'm a little bit surprised you didn't try to phrase it as something about special commutative Frobenius algebras or something like that.
Well, that's what separable algebras
very possibly
basically are.
But what am I trying to say? That well, before we get there, let me try to keep answering the question.
Sure. Yeah, I was just getting impatient because I mean, actually, it was extremely helpful what you said, but it's because it's helpful. Sure. It immediately makes me want to charge.
Sure. But there's more. More useful stuff to say. So what I'm trying to say is, so far I just gave one way that you could try to understand the fundamental group of a space, and that is, like we say, the right. I mean, you have lots of choices when you're trying to understand an object. You have lots of choices. Well, the general philosophy is to understand objects by how they map into other objects, and or vice versa, how other objects map into them. But you get a lot of choice as to which objects to map into or which objects to map out of. And, right, one of the answers is, well, map into all of them, or map out of all of them. And that's, in a way, that's kind of what we're doing when we say, look at the G torsors for all different G, right? Because G is a parameter we can vary, so you kind of looking at all the groups that we can map into, I guess, when we're looking at G torsors. But there are other interesting choices that we have. So, for example, right, you can sort of, again, there are technical questions here about whether we're dealing with an arbitrary discrete group or a profinite group, but let's try to sweep that under the carpet for a moment. But the idea is that for some reasonable kind of group, you can completely understand that group just by homming it into the symmetric groups. You don't have to hom it into all groups, just hom it into the symmetric groups.
Mm-hmm.
And that means that instead of looking at principal fiber bundles, you're really just looking at covering spaces. And again, one of the things that you can do here is, right, we're saying covering spaces, we're saying symmetric groups such like n bang. And, again, depending on whether we're doing abstract groups or profinite groups, you could consider n being finite or n being arbitrary cardinality or whatever. But we're focusing more towards the finite end of the subject at the moment. And so, n is a parameter that we can vary. So, you can say that you're homming this fundamental group into all different symmetric groups, or you could, use some sensible, slick, philosophically good thing that says we're actually just homming this fundamental group into the groupoid of sets, or the groupoid of finite sets, or something like that.
Mhm.
So, but it's helpful to think of it as homming a group into a groupoid. Expand your view to include groupoids, and then there's this systematic thing that homming a groupoid into the groupoid of sets gives you something like a topos, a Boolean topos, something like a Boolean topos, or something like that, that as a Boolean topos, or some nice kind of topos, knows all about the group. That it's a good way of, you can encode the whole group into that topos. And that's part of the philosophy of this Grothendieck's philosophy of Galois theory. From that point of view, there's a bunch of things that are going on, right? Which is, first of all, you're suppressing the need for looking at all different G's, for considering G torsors for all different G's. You're sort of getting away with not having to consider that many different G's. You're just using the n-bangs, and that's giving you all there is to know about this group by getting this topos of whatever we call them. And what do we call? So these are probably something. So, right, these are right here. You don't have to worry about saying what the automorphism group is or anything like that. You just say that these are the nice commutative algebras, where nice means something like separable or special commutative Frobenius or something like that.
Yep. And then if you want to be precise, you need to say continuous actions on finite sets of this profinite, of this Galois group with its profinite topology. At least that's the way people usually get the details to work out. I'm happy to not worry about those details right now much. I've been busy studying them.
Yeah, we don't have to worry about those details right now. They actually are easy to take care of. I think that's why we don't have to worry about them. They're easy to take care of when you do them the right way, but we don't have to do them the right way. So right. So part of what we're saying is that you have a free choice here. You have a lot of aesthetic freedom. You can, if you want, you can know all about the fundamental group by just knowing how it maps into the groupoid of finite sets, basically, or the groupoid of sets, or something like that. But on the other hand, you can, go in this different direction and know all about the group by knowing all about the principal fiber bundles for all different G. And, so either way, you're studying the same subject, but it could just lead you in different directions. Art and reciprocity or something might lead you in some particular direction where, it's actually useful and fun to focus on a particular choice of G that's like some finite abelian group or something like that. And that's part of what I was doing when I was focusing on Z mod 3 torsors. But so the aesthetic freedom idea is that part of the idea is that in principle any of these foundations is good enough all by itself. And, whatever you're doing with any of the other foundations, you could translate it into the foundation that you prefer to work with. So, right at some point today, you've already been thinking out loud about some of that work, of how to translate one of these foundations into the other foundation or something like that. So, right, you could try to say, how do we translate the idea of, G torsor? How what does that amount to if you're thinking in the foundations where you just think about the topos of the continuous actions of the profinite group or something like that. And it's something very straightforward, right? So what were we trying to say? Can we just think about that for a second? So, if you've got the topos of G sets, and again, I'm trying to ignore whether we're thinking about finite G sets or profinite or whatever, continuous or whatever. But if we've got the topos of G sets, then we could talk about, and let's say we have another group H. Well, let's see. Agonizing over what letters to use here. What's a good letter for a fundamental group?
I won't say pi because you don't consider.
No, you can say pi. Okay, we'll say or P or pi or something like that. Okay, so pi. And on the other hand, a good letter for a group is G. So we'll consider G torsors, but over this space that has, or if you prefer principal G bundles, over this space that has fundamental group pi. So we've got this topos of pi sets, right? And so what are the G torsors from that point of view? So they're just, as soon as right. Let's see, what are they? Don't That's a good question. Let's see. They really are just, homomorphisms from pi to G, but I'm trying to think of some way to say this. Let's see.
Are you trying to make?
They should be just abstract models of the theory of, okay. So that's what they are. They are actual G torsors that are acted on by pi. Is that what they are? Yeah, they're G torsors in that topos. So a G torsor in that topos, if I'm not screwing up, we're sort of working in the doctrine of toposes here or something like that. So it would basically be, an ordinary G topos in the category of sets, which is just,
You said G topos, but you meant.
Sorry, G torsor. An ordinary G torsor in the category of sets, which is basically just like a copy of G that's lost its base point. But, it's lost it in a right-handed way or perhaps a left-handed way, but you have to be careful about which direction it has forgotten its base point in. So it's one of those things, but it's in the topos, in the topos of pi sets. So it's got an action of pi on it. And yeah, and right. And if you work that out, that actually means that it right. And maybe to if you want to specify more carefully about what that means when you're checking to make sure this all makes sense. I hope I'm saying this right, that it's, this action of pi, it's not acting on, I'm saying this right, it's not acting on the group G. It's just acting on the G torsor, which means it's really giving us a homomorphism from pi into G rather than a homomorphism from pi into the automorphism group of G or something like that. If I didn't make any horrible levels up there, then I think that should be the right way to do it.
I think you can think of it as homomorphism from pi to G, which gives a way for pi to act on G by say, left translations, randomly picking one there. And then G still gets to act in a commuting way by right translations. And so then you get so that's how it gets to be a torsor, a G torsor. But it's a G torsor in pi sets. Yeah. So that sounds right. I mean, that's one way to
yeah.
And I guess another way to think about it is it's like a principal G bundle over K pi 1.
Yeah. There's probably all sorts of ways of thinking about that. So it's like, right, it's a set that's acted on by two groups and, in ways that are commuting with each other or something like that. So it's like a bi action or something like that. But with respect to G, the action is, very torsor-like, but not with respect to pi. So, the action could be very trivial with respect to pi, or it could be very non-trivial, or anything in between.
Yeah.
Yes. And so, okay. So right, I'm trying to, like I said, I'm trying to give you more and more answers to your question of why torsors. And
yeah, I would be,
you don't need all these answers because you can convert one answer to another. But yes, go ahead. What were you saying?
I would be incredibly frustrated if I hadn't been spending a lot of time trying to learn Grothendieck's approach to Galois theory, where a chunk of it involves translating these sort of group theoretic or topological covering space concepts over into sort of algebraic geometry concepts, or not, I don't know if translating is even quite the right word, but connecting to that. So like when I was asking my question originally, like today,
yes,
I was frustrated because I felt I didn't understand how it was connecting to I'll call it algebraic geometry, but I could call it like Galois theory. The Galois theory in the sense that like you care about fields and field extensions and stuff like that, or separable algebras or whatever. So you're still not talking about that, but luckily I know enough so that I can start taking this stuff you're saying and plug it into that. And that's sort of, I mean, the homotopy theory side of things is very nice, and I sort of understand it. And so the intriguing stuff is the stuff that I haven't until recently understood, which is everything about Galois theory and fields and field extensions and art and reciprocity and all that stuff.
Yes.
So I'm hoping that you'll eventually start moving in that direction, but I'm saying that I can actually sort of do that myself too, somewhat.
Right. All right. So let me try to say a little bit more about, a little bit more of all the answers to this question. So, we have Grothendieck's philosophy of Galois theory, and part of that is this fundamental theorem alleged fundamental theorem of that philosophy, which says, maybe we've already come close to stating it in some sloppy form, that the category, the topos, or something like a topos of something like a Boolean topos of nice actions of this algebrogeometric fundamental group of like the spectrum of a field or something like that, that it is that Boolean topos is equivalent to some topos that you get by actually, making this category of some kind of algebras over the field that you're looking at.
Mhm.
So by the right, and so again, this is already answering, or should answer, one of the questions that you're already asking, which is sometimes you're asking about why am I looking at not just field extensions, but more general algebra extensions? Well, it's because in that whole fundamental theorem, you have to consider, the extensions that are not just field extensions, right?
Yeah, no, I wasn't. I knew that. Yeah, I was just wondering what's this result about G torsors,
Okay.
and I think I can say it now, but I won't.
Okay.
Because I already
Okay.
did, actually. I already did.
Okay. But another thing I was trying to say here is that right. So this fundamental theorem gives an equivalence of categories, an equivalence of something like Boolean toposes or something like that.
Yeah,
exactly
that.
Well, I get confused because somebody said something about a Boolean pretope, or I don't know.
That was this more general. That was
Okay.
this carbony stuff about separable monoid objects in a more general.
That could be eventually relevant, but I'm not going to worry about it right now. But what am I trying to say? That it gives you an equivalence of categories between just, on the one hand, some abstract category of nice group actions, and on the other hand, some somewhat more concrete category of some kind of algebras of a field, or maybe of a ring or something like that that you're studying. And so you're getting an equivalence of categories that way. But one of the things that can sometimes get annoying about that, particularly if you're really literally working over a field, is that that category that you're studying can get a little bit annoying, because in that case, this moral fundamental group can be seriously profinite and can be annoying in that way.
Mhm.
Right? Why am I saying that it's annoying? Well, because the actions of a profinite group, the category of that actions, it's a little bit like lumping together the category, all the different categories of actions of all these finite quotients of this profinite group. So it's like you're, throwing everything in together, and it's more than you need, so it can get annoying in that sense.
Yeah, I was thinking that some modern mathematicians should start deciding that that's like a old-fashioned way to do things.
Well, there are various, but there's more than one way to get around the problem. Or are you suggesting a particular way to get around the problem?
Yeah, I think you're almost sort of saying it. One way is just to sort of think about all the different finite quotients of this. I mean, this profinite group is this big universal receptacle for a whole bunch of groups and homomorphisms between them. And so maybe you should just like work directly with the groups and the homomorphisms between them.
Yes, if I understand what you're saying, yes, but there's more than one way of doing that. So what am I trying to say? So, see, the very minor elementary point I'm trying to make here is that this fundamental theorem is giving you equivalence of categories. But a torsor, instead of giving you an equivalence of categories, it just gives you a functor between categories. So instead of exploiting a sort of an annoying equivalence of categories, annoying because it's connecting perhaps these very annoying things that involve profinite things, you can just work with these torsors, which is like it's so you're mapping your profinite group into some specific finite group G. And so you're working directly with the category of actions of the finite group G. And that's in some sense, can be much less annoying to work with, because it's not, everything thrown together. It's just this one thing. So, right, it's just a trade-off, between, instead of working with an equivalence of categories between annoying gigantic categories, you can work with a functor between categories. And, the functor may connect one of these gigantic annoying categories to one of these less gigantic, less annoying categories. So you see what I'm saying? The torsor is from a certain point of view, the torsor can do similar things for you as what the fundamental theorem does, except that instead of giving you an equivalence of categories, it's giving you a functor between categories, and the functors and these the categories involved between these functors could connect an annoying category to a less annoying category. So that could be a useful thing to do.
Can you just say what those are now? In some.
Well, I mean, so an example is, like if I have, let's say I have, let's take like the absolute Galois group of the rationals.
Mm-hmm.
And in some sense, that's, last time I checked, but maybe even still today, people would consider that to be an annoying group in some ways, in the sense that, what was the annoying fact that somebody said, or that I don't know when they said it, but I read it recently, so maybe it's still true, that nobody knows any elements of that group or something like that, or nobody else knows any non-trivial, in some sense of non-trivial elements of that group or something like that. Because, they know plenty of elements of the group at these finite levels, but if you go all the way out, somebody was claiming that they don't know how to, although, right, I guess there are all sorts of fancy conjectures that do conjecturally tell you what some explicit elements of the group are. But they were claiming that without those fancy conjectures, it was hard to even name a non-trivial element of the group. And in that sense, it could be an annoying group. Yeah, maybe some of those fancy conjectures are theorems by now. I don't know. But, I was just trying to illustrate what annoying is supposed to mean here. So there's this, annoying absolute Galois group of the rationals, and it's sort of annoying topos of continuous actions, which is, all these special commutative Frobenius algebras over the rationals, or something like that. And, because it's huge, it's got, all this variety, all the algebraic numbers in the world, they all participate in this, or everything thrown together. Whereas if you're just, if you're just studying some particular Z mod 3 torsor over the rationals, which is one of the things I sometimes do, then like we said, then you're not dealing with that whole gigantic thing. You're just focusing in on some little finite 3-element quotient, perhaps 3-element quotient of this ridiculous pro-finite group. And, at that point, you're just dealing with the actions of the cyclic 3-element group. And that's a very concrete, topos. You can draw little pictures of the objects in that topos on paper, and you draw very complete pictures of the objects in the topos. Whereas,
okay, so now the question but the question I had is like, so if I've got so you're just talking now about, sorry, what are you talking about? You're just talking about Z mod 3 sets. That's this topos.
Yes, and the functor that you get So you get a functor from Z mod 3 sets from you get the right. I mean, that's what this torsor is, right? From this Tanakian viewpoint, the torsor is this functor from the Z mod 3 sets to the special commutative Frobenius algebras. Well, you can think of it that way.
So you had picked,
Yeah.
I'm getting confused. You had picked the specific homomorphism from the absolute Galois group to Z mod 3?
Yes, that's one way to do it. Yes.
So I mean, that's how you get started. And so then now any Z mod 3 set gives you an absolute Galois group set.
Yes.
And thus a special commutative Frobenius separable algebra over.
Yeah, so this is a very coarse approximation to this
that's fine.
bigger topos. And so you can do that in a lot of problems. In a lot of problems, you can say, well, I don't care about any extensions beyond this.
Okay, but that's fine. But okay, now like suppose I do that, okay.
Yeah.
So then I believe that the transitive Z mod 3 sorry, you picked the specific homomorphism from the Galois group to Z mod 3. So can you tell me one specific one, for example? So
yes, I mean there's the it's how do I say this? It's the Z mod 3 torsor of, I want to say the, am I saying this right? I want to say something like the ninth roots of unity. What am I trying to say? Well, I mean, this is one of the things I've been struggling with. I mean, there are very easy answers to that question, but I'm still struggling with being able to phrase those. If we switch it, I mean, we could switch it to being like a quadratic extension, and then it's a Z mod 2 torsor.
okay, so
it's ridiculously easy to talk about. That's the way of short-circuiting some of the annoying questions here.
So 3 is still too hard.
It's too hard in the sense that it would take me a bunch of hours to answer or something.
Hours? Okay, that's weird. Okay, well then let's do.
Well, I mean, partially because there's a whole bunch of Mathematica programs and things that I'm supposed to be finishing writing, which will help really answer those questions. So you can sit here and watch me write those programs or something like that.
But I mean, you should see. Shouldn't you be able to? Should you be able to? Am I really confused? Should you be able to get one from any field from any field extension of the rationals whose Galois group is Z mod 3?
You can, yes. It's just slightly annoying trying to explain how to actually calculate those. And it's annoying right now because one of the things that's annoying now is because I know that in principle there are non-annoying ways to do it, but I haven't gotten to the point where I can slickly tell you it's non-annoying.
Okay, well I'm willing to just sort of say, here I've got some algebraic number field whose Galois group over the rationals is Z mod 3. Don't ask me what it is.
Well, you know what? If we switch to Z mod 3 torsors over the Eisenstein field, then it's really easy to say what these Z mod 3 torsors are. They're just gotten by taking the cube roots of basically anything.
Okay. So we take the Eisenstein field and adjoin a cube root of basically anything.
Right. Cube root of 13 or.
A cube root of something that didn't already have a cube root. Yeah.
Well, you can also do the cube root of something that does already have a cube root.
Oh, okay. Then you get these, yeah.
That's where you get the trivial torsors from. So,
okay. So I pick a field extension of, I start with a field. I pick a field extension whose Galois group over that field is Z mod 3.
Yes.
That I now think of.
Wait, can you just let me just make sure I'm listening as carefully as I should be. Can you repeat what you said?
Okay.
You have what? You have a field, like for example.
I pick a field, which for you just a second ago is the Eisenstein.
Agreed. Okay.
But I pick a field, and I pick an extension of it whose Galois group over that original field is Z mod 3, for example.
Yes.
So now that gives a way for the absolute Galois group of my first field to act on this extension in a way that factors through Z mod 3.
Sorry. I'm just thinking, right at the moment I'm doing a terrible job of listening. Could you just say it again? And I'm really trying to listen here, but I'm just struggling at the moment. Go ahead.
Okay, maybe I'll make. Should I make up? I'll make up names for two things. Well, one of the, we pick a field K. That's our field K. Okay.
And that's going to be the Eisenstein field.
Well, I want it to be general, but we can pretend it's that.
Sorry, I'm just struggling to find my cursor here so I can write things down as you're saying them.
So we,
sorry. Okay, so you got
pick a field K.
And is it secret? Is this example secretly the Eisenstein integers or not? This is the cubic extension. We're not sure.
Secret. I'm not kidding. That's between you and yourself.
Okay.
You just. Yeah. I mean, yes. That could be it.
Okay.
Then pick any extension of K, say L.
Yes.
And I guess I want it to be a Galois extension. And so I wanted the Galois group over K to be Z mod 3. So Gal L over K is Z mod 3.
I always have to stop and again. I fall into stupid traps here about what a Galois is. I mean, the Galois extension is in the Galois correspondence. It corresponds to a normal subgroup or something like that.
Yeah, and that actually is important. Yeah, that actually is important.
Okay.
For what I'm about to do next. Thanks for pointing that out.
Okay.
So what I get is a homomorphism from the absolute Galois group of K to Z mod 3. This has given me that.
That sounds right. But
and that normalcy was important. So we've got a that's what's making there be this homomorphism from the Galois group of absolute Galois group of K down to this Z mod 3, or modding out by a normal subgroup.
That's right.
So, okay. So yay, so we've got a homomorphism from the absolute Galois group of K to Z mod 3, and that is what you're calling a Z mod 3 torsor. I don't know what you call it, over something, over
okay.
K.
Yeah.
Over K.
Or over the spectrum of K, I don't know. There's all sorts of different ways of saying. Yes.
So
is there something in what you just said that is going to make it clear that there's like a order 3 thing here?
Yeah, I mean, I said the absolute Galois, sorry, bleh, the Galois group of L over K is Z mod 3. So Z mod 3 is acting on L in a way that fixes K. So
Maybe I'll
there is
just, I'm maybe got some silly ad hoc name A for this, unless you have some notation that shows that it's
that's fine. A cubed equals 1. Uh-huh.
A cubed equals 1, right? And I'm not guaranteeing that A isn't 1, but A cubed is 1, yeah.
Yeah. Well, I guess I was asserting that A was not 1 because because the Galois group of L over K is Z mod 3. So I can pick a generator and that generator will act non-trivially.
Oh, okay. Let me see what you're saying. So right. I mean, right. I mean, we said, okay, maybe I didn't catch everything you said. I mean, we said that a torsor is sort of just a homomorphism, but somewhere along the way, you built in the assumption that this homomorphism is surjective.
Right. Yeah, I mean, I wasn't starting with the torsor in my mind. I was starting with this field extension, and then I noticed.
Yeah, and I'm just bringing out the fact now that you could have non-surjective ones, and then
right, right. So now,
and that would still give you one of these pictures, but the only thing that would be different would be that you still have A cubed equals 1, but you just don't have the guarantee that A isn't also 1.
right.
Okay. And
So
in that case, L isn't going to be a field. It's probably going to be an algebra or something like that.
Right. Let's see. Now I'm getting demoralized again because I don't see what we're. So now we've got this Z mod 3 torsor over K.
And it can be drawn as a picture like this, although there's probably, implicit properties and things here. But yes, go ahead.
So now I'm getting demoralized by saying, like, okay, so what do we do with this torsor?
Yes.
I guess maybe because I started from already having pretending I already have the field extension. I don't know what more I get out of having the torsor in this case. Maybe it's because I started from the other end.
Well, I mean, I'll just repeat what I said before, that, in the homotopy theory analogy, the field extension is basically, some kind of space over the base space. But, because it's a nice extension, it's actually just a covering space. So you've got a covering space, whereas the torsor is a principal G bundle with discrete fiber, right? So there's this, in homotopy theory, this is sort of one of the really easy parts of homotopy theory, because we're only dealing with very low homotopy groups, the fundamental pi1 rather than pi2 or anything like that. And, there's just a straightforward interplay between, on the one hand, covering spaces, and on the other hand, principal fiber bundles with discrete group. And you're just reproducing that story here. And, I don't think there should be anything terribly demoralizing about it. It's just that it is a very straightforward thing.
Yeah, well, that's what's demoralizing about is that I'm not getting anything out of it yet.
Yeah. So right. So I mean, in reaction to this prodding that you're giving me here, maybe it really is true that this is so straightforward that maybe it's so straightforward that you don't see much point to it. Maybe until we do get to things like the reciprocity theorems or something like that. I mean, I'm just making this up now, and to try to defend myself from your attack here. But maybe it's true. I don't know. It's just a very automatic way of shifting viewpoints using abstract nonsense. But it is going to be useful. I mean, let's we're getting very close to quitting time here, so maybe this is not a good time for me to say too much more about this. But you know, I am tempted to try to show you examples where, you know, I do very concrete stuff that helps me to understand the field extensions. But the thing that really helps me to understand it is applying these principles that we're talking about here about, you know, the relationship between torsors and field extensions and so forth, torsors and field extensions and special commutative Frobenius algebras, et cetera, et cetera, et cetera. Again, a lot of this has to do with the art and reciprocity.
Yeah, I'm wanting to
well, maybe I'll just
continue on into that.
Yeah, I mean, maybe I'll just try to. Again, I can't really go into that whole thing right now, but maybe I just give a little bit of a hint about it. And again, this has to do with the way to repair one of my mistakes from a previous discussion of ours. Not sure mistake is the right word, but one of the things I didn't understand from a previous discussion of ours. So in a previous discussion of ours, I was trying to develop a very concrete way of writing down these Z mod 3 torsors. So I think I was writing down things like, I was actually looking at Z mod 3 torsors over Q. And that was sort of making it tricky, because if I had been, you know, if I had been doing Z mod 3 torsors over the Eisenstein field, it would have been very automatic. But I was trying to back up and do Z mod 3 torsors over the rational field. And that was making it a little bit more subtle. But I was, you know, trying to have pictures like this. So how does this work? What am I trying to say? I'm trying to say something like, yeah, okay. So I have Q adjoin X sub 1. Okay, I'm going to join these two variables, X sub 1 and X sub W. And then I put in a relator here, and it says that X cubed is equal to, well, maybe I should say X cubed is equal to, I was going to say 1 to the power of 1/3, meaning a primitive cube root of unity. But I'm going to say X cubed equals W. So I'm using W as a peculiar abbreviation for our favorite primitive third root of unity here. And so I put this relator in quotation marks because it's supposed to be sort of telling us to do something formally. It's telling us to form this number X, which is X1 plus X sub W times W. And then to interpret this equation of its cube being equal to W, interpret that formally in terms of, yeah, in terms of the formal primitive cube root of unity, which we call W. And so there's that field extension. Well, I was going to say field extension. I guess it's an algebra extension. It's an algebra over a field. And I guess it turns out to be a special commutative Frobenius algebra or something like that. But I had been hoping that, well, okay, I had been hoping that this was going to end up being a Z mod 3 torsor, that there was actually a thing like this that would make this into a Z mod 3 torsor, because it's related to cube roots, and cube roots are related to Z mod 3 torsors.
Mhm.
And if you can remember all the way back to that previous chat we had, that guess of mine turned out to be not quite right. This is not a Z mod 3 torsor. And if it were a Z mod 3 torsor, then this algebra here would be a 3-dimensional algebra over the rationals. But this is, in fact, a 9-dimensional algebra over the rationals. And so I struggled with this a whole bunch in order to try to understand how to turn this into a Z mod 3 torsor. And I think there's still some things that I don't completely understand about this, but I made a lot of progress with it. And I really want to show you that progress, like hopefully next time or something like that. But I want this to be true even more, but it's already true to a great extent that in my understanding how to do this, and in my understanding how to develop a nice big conceptual picture that makes it easier to do these gritty concrete calculations. I really find myself trying to use, and to some extent successfully using, Grothendieck-Galois theory and the fundamental theorem, but also the torsor concepts. And connecting it to the Grothendieck-Galois theory, and connecting to the special commutative Frobenius algebras. So, right? I mean, so an example of one of the kinds of things that I want to do here is this is some kind of 9-dimensional algebra over this thing, and it turns out it's the right, it is like a separable algebra or something like that, whatever the property is that it needs to have in order to correspond to an element in this topos. It is that kind of object, and I think that means it actually corresponds to some 9-element action of this group. And I was trying to clarify what this 9-element action is, and then trying to clarify how to use all sorts of, topos operations.
So 9-element action of Z mod 3.
Say that again?
A 9-element action of Z mod 3.
Yes, but I think it's actually right. It's what it's. Again, I'm not running out of time here, so I don't have. I'm probably not capable of giving really clear answers to these questions because I don't have the answers clearly in my mind. But I think it's one of these situations where we have one of these bi actions. So, like it's on the one hand, it's acted on by the absolute Galois group of the rationals. On the other hand, it's acted on explicitly by Z mod 3. And those two actions are sort of commuting with each other. I think that's what's happening. But then I'm, trying to perform, I'm trying to use some of the operations that live on a topos to extract from this 9-element action of a group the 3-element action of the group that's actually supposed to be the torsor, the Z mod 3 torsor. And so I I've made a lot of progress in understanding this example, and this is one of the examples that I hope to demonstrate to you, perhaps next time or whenever, where we'll see in action some of these concrete philosophies that we've been trying to explain today. So,
okay.
So is there anything else we should try to do before we quit here for today?
I'll just mention that earlier in our conversation, I was talking about sets that are torsors of G on the one hand, but then also acted on by this other group that we were calling I at the time.
Yes. Right. That's going on here, I think. Yes. Go ahead.
Yeah. So that's good. That's what I hoped.
Right.
Okay, no, I think things makes a lot more sense now.
I hope so, but I hope it'll be really get clear when we really see, you know, these principles in action applying to concrete problems.
Yeah, no, that's when they'll be not only clear but fun.
Yes.
More
Something
fun.
like that.
Yeah.
Okay.
Okie doke.
Okay. I'll see you.
Yep. See ya.
Okay. Bye.